So we're saying that we've got amazing sessions, and you probably have heard about a company that was born more than 20 years ago in Barcelona. It's basically based in Barcelona and Boston, and you probably heard this word, Neuroelectrics. You probably heard about this as one of the major innovation projects here in Barcelona. Neuroelectrics products are being used worldwide for basic neuroscience and clinical research in hundreds of universities and academical and medical centers. Clinical applications are already being developed and diagnosed to treat brain diseases and improve brain health, such as epilepsy, depression, Parkinson's disease, Alzheimer, and many others. And they're actually working right now to combine that into the AI tool. You probably have heard, when talking about Neuroelectric, you probably heard about one of the members of the company, one of the visible members of the company. Many of them are in the company, but probably you've heard about Anna Maikes, who we're all in love with, and she's very connected to this ecosystem. She's been this morning talking upstairs, and she'll be tomorrow again. And we know a lot about her. She's the CEO of the company. She combines this knowledge in terms of the economic side, but also about the company. She explains it's everywhere. We've been connected in many studios many times, and she's great. But there is another 50% of the company that today we're proud to present to you, because I'm sure you'll also fall in love with him. He's like the scientific 50% of the company, and he's, the brain side of Neuroelectrics. So it's a pleasure this year to invite to join the stage to Giulio Ruffini from Neuroelectric. Giulio, whenever you want, floor is yours. Thank you.
Good afternoon, buona tarda. Yes, I'm the one hiding behind in the office normally, so I will try to entertain you today. Okay, so the title of the talk is, as you can see, Our Quest for the Mind's Blueprint for Therapeutic Applications. And I should say that my background is theoretical physics. I started in theoretical physics, migrated to neuroscience over the years. And this will explain a little bit some of the parts that I will talk about today. So my fascination began as a theoretical physicist with the electrical character of the brain, with the electrochemical character of the brain. And the fact that this complex organ is computing all the time, and it uses something that physicists know very well, Maxwell's equations, and some other things. So the first question is, how do these patterns, what do they have to do with the mind, with the experience, with consciousness, and can we use, if we understand how that works, this for communication and therapy? So after a few years of work, we created Neuroelectrics with a focus on therapy, rather than brain-to-brain communication or things like that, because there's a large number of patients out there in diseases, disorders such as Parkinson's, with depressions and Alzheimer's, and I will be talking some of these cases as we go along. We developed a technology early on that allowed us to read brain activity from the brain, so this electrical activity in the brain. And soon after that, we realized that we could actually write into the brain. So this is called brain stimulation. And we developed a technology which is, as you can see, consists of multiple electrodes. You apply it to the brain, and it allows you to deliver electrical currents which create electric fields in the brain and gives you quite a bit of power compared to other technologies out there. But there is a question. The question is, how do you use it? And this is not a trivial question, of course. So if we want to help patients with neurological conditions, what can we do? So the first thing to notice is that the brain is a plastic network. It's a large dynamical system, a complex one. You can see here the human connectome, the wiring inside the brain. And as you can gather, it's fairly complex. And with electrical stimulation, what we can do is create electrical fields that, in parts of the brain that we want, that can alter the excitability of these parts of the brain. Or we can actually do entrainment, so we can actually generate oscillations or support oscillations or disrupt oscillations. And the fun thing is that you can not only change the dynamics of the system while you apply it, but this has plastic effects. So this actually leads to change in the connectivity in the brain, and that will alter function in the brain. So you can use it for therapeutic purposes. However, each patient is different, and the question is, how do we optimize the stimulation for each patient? Each pathology is different in nature, but also each patient is different. So we need this concept that we call Neurotwins. And the idea is to do our work, since day one when we created the company, was to use this in a science-based way, not just trial and error, but actually trying to understand how the brain works and use that knowledge to actually adjust brain stimulation. So in order to create a neurotwin, you have to do two things. One of them, you can see on the right-hand side, is the biophysical model of the brain. So the brain as a physical system, you want to send currents through it, you want to read out whatever it's doing, so you need a physical model that couples your technology and the brain activity with measurements. And the other one is that you need a physiological model. You need a model that describes how the brain works, as a network, as a dynamical system, right? And you can put these two things together, and you have the complete neurotwin of the patient. The modeling, I won't bother you too much with the details, but it involves studies across scales, from the microscopic to the middle scale to the macroscopic scale, trying to join together these two worlds. So in the process of personalization begins with a patient and with the patient data. This data is assimilated into this model, this neurotwin model for the patient. And once the model is created, we can actually, in the computer, find out what the best way to stimulate the brain is. We can do simulations and find out where to put the electrodes, what currents to use, to change the system in the way we want. And after that, after the stimulation is delivered, and this is normally done through several sessions, sometimes months, for a few tens of minutes each day, we can gather pathological biomarkers of the patient from EEG or other means, and follow up the patient and adjust the stimulation. So here's a short movie that shows how the process begins in the case of epilepsy. So we have a doctor that defines a problem area in the brain, a target. The patient is sent into an MRI scan where data is collected, structural data in this case. The doctor then paints a target in a model of the brain of the patient. And once we have this, we create the neurotwin model. In this case, it's a biophysical model. We use deep learning techniques to speed up the calculations. We develop the electrical field of the model of the system using finite element methods, and then we optimize the protocol using genetic algorithms. And finally, a custom cap is created for the patient, and the treatment is applied. In the case of epilepsy, we have, which is where we began, because epilepsy is a very physiological disorder. It's a neurological disorder, and it's quite well understood what is wrong. It's normally focal. We work in focal epilepsy. So it was a first test ground for the technology. And after some work in Boston, and also with colleagues in Marseille, we have done several pilot studies showing that we can reduce the occurrence of seizures by a clinically significant amount. This is now leading to a multi-center clinical pivotal study, which we're carrying out in Europe and the US. We will have results in a year or two. We are also carrying out studies with the same type of technology in epilepsy, but this time with physiological models in implanted patients. This is a smaller set of patients, but this implantation of SEG allows us to collect more data about the problem and to create more personalized models, so it's an interesting future technology for us. And we're also doing tests, pilot studies now in Alzheimer's disease, where the stimulation is alternating current stimulation in this case, to try to recover fast circuits which are damaged in Alzheimer's. This is a home study, so patients are being stimulated for 2 months at home with our technology. And we should have results of this randomized controlled trial next year. Okay, so this was the first half of the presentation. I don't have a view of the timer, but I think I'm doing fine. So now we shift to psychiatric conditions. So I've been talking about neurology, now I would like to talk about psychiatry. And the first question is, what is the difference between these two words, right? So neurology is primarily concerned with the physical and structural aspects of the brain and pathology in the nervous system. On the other hand, psychiatry focuses on the mental, emotional, and behavioral aspects of well-being. So it's also related to brain function, but this time it's about experience. It's a pathology of experience. So this reflects a gap in the field. The fact that we have these two disciplines reflects a gap in understanding where biology connects with experience and consciousness, emotions, and all that, right? The future, I think, is where these things will come together in neuropsychiatry. Actually, computational neuropsychiatry is probably the future. And this is what I would like to talk a little bit about now. So in major depressive disorder, which is a large prevalent disorder with many millions of patients globally, there are few solutions, from pharmacological solutions or from other brain stimulation technologies like TMS or ECT. So it's an underserved patient population for sure. From the mechanistic point of view, what we know is that there are some areas of the brain which are hypoactive in depression and others which are hyperactive. And this has provided the basis, the rationale for stimulation studies so far. So in particular, the left dorsolateral prefrontal cortex, approximately here, is the area which is hypoactive, and brain stimulation studies which have been done to date have attacked this area. And ourselves have done the same in the pilot studies and shown that you can get an improvement in the depression scores of these patients stimulating here. However, this seems to be like the tip of the iceberg, because we have identified one area that some studies have shown some promise, some rationale behind it, but it's still not very well understood. And in fact, you can try different montages that give you approximately the same results, and we don't really know what is the best way to do this. So the question is, can we do better? How can we do better? How can we stimulate patients with depression in a more effective way, right? So this brings the question, which is a very interesting question, is what is depression? And the first thing that one finds out when trying to learn about this is that it's not a single condition. It's actually a syndrome of many conditions with very diverse etiologies, so different causes that can lead you into this state. The defining feature of depression is that it's characterized by a first-person experience of sadness, hopelessness, and a lack of interest in pleasure. And here the key word is experience. So that's what I was referring to before in psychiatry, that it's about experience. The experience machine is damaged. And here we have the case at hand. It's not the only psychiatric disorder with this characteristic, of course, but it's a very salient one. So the question comes that has been asked many times is, how can this feel? How can a brain, the physical system like this, feel at all? And it seems that in order to really understand how to treat depression, we should really look at this question as closely as we can, not to mention of all the AI stuff that is happening, which I will mention in a moment. So in order to do this, I want to take you into a brief detour into defining experience and consciousness, and a brief introduction to what they call cosmograph theory, which is a theory that I have developed with coworkers for the last 25 years, which is a theory of consciousness. And it can give us definitions and a working handle on the definition of emotion and depression and the role of valence. So where do we start with cosmograph theory? I would start with the elephant in the room. And as I mentioned, the elephant in the room is that who are we? What is experience? What is this experience that we have? And as curious humans and scientists, we have surely been asking these questions since we were, from very young age, and we probably put them aside at some point, like science did since Galileo, because they were very hard. But in fact, these are the questions, I think, that are of primary importance to any scientist, and we should not avoid them just because they're hard. And one aspect about this problem is that it's normally posed something is conscious or something is not conscious, and this is a false boundary. There is no such boundary. In fact, there's a continuum, and in this plot here you can see a depiction of in two axes. One is the level of consciousness in the x-axis, and the content, the structure of consciousness in the y-axis, and you can hear a representation of different brain states, human brain states, right? You have sleep, you have anesthesia, you have wakefulness, you have fetal consciousness, you have complete locked-in syndrome in this kind of diagram. This diagram was proposed by researchers in the Edge some 10 years ago. You can do the same with different species, actually. You can start thinking, okay, I'm human, there's dogs, there's turtles. Those of us who have pets know that they are definitely conscious. And you can probably put them in this diagram. And at some point, you start asking, where does it stop? Where does the conscious experience stop? And, well, this is the famous hard problem of consciousness, as identified by David Chalmers some years ago, and many other philosophers before him, but never put so blatantly in paper as he did. How does the water of the brain turn into wine of consciousness? This question. And in KT, we start with a premise. If there is no boundary that we can identify where consciousness begins and ends, the answer is that there is no such boundary. There is nowhere a boundary. And we postulate that there is experience everywhere. Okay, so this is a feature of reality is experience. If you're interested in this topic, I encourage you to read this book by Philip Goff, Galileo's Error. It's a fascinating philosophical description of this. And I would like to distinguish two words now. Not talking about this word consciousness, which is loaded by experience, pure experience, and by that I refer, what is it like to be you? What is it like to be without any other attribute? And this was a very famous essay by Thomas Nagel, actually there's a misspelling there. What is it like to be a bat? Where he reflected about this problem of what is it like to be, and identifying this as experience. There's some basic notion of experience, which contrasts with what I think we need to work on, which is structure experience. The spatial, temporal, and conceptual organization of our first-person experience in the world and of ourselves in it. So this is the structure that we perceive in experience. It's not the same thing as experience, but it's the structure on top of experience, if you will. So the theory, in a nutshell, says, if there is experience, what leads to structure experience? So assuming that there is experience, what is the structure experience? And the answer is given in 3 steps. So first, we are agents, as I will define in a second. Agents run models of the world, and because of that, enjoy structure experience. The models is what give structure to experience. And the last point, which is important here, is that agents have goals, and this is the origin of valence and emotions. So quickly, what is an agent? It's a computational system that uses compressive world models, models that compress the world and that can actually generate data from the world, the generative world models, if you will, in the language of machine learning, an objective function with goals, and a planning engine, something that allows it to make plans to maximize the objective function. So I have a model of the world, I want to maximize my pleasure, and I use planning to do that. Here's an example of a futuristic agent, but you can find many other ones around you. So a model, more precisely, is a program that allows you to compress information. You can also say that it's a simplifying rendition of reality. And you can also say it's a mathematical object. It's a mathematical object because a model is computation, needs computation, and therefore it's dynamics. The brain computes, it's a dynamical system. And for those of you who have taken some math, dynamics is a branch of mathematics, and it also has geometry. And here's a kind of a rendition of that idea, in which brain dynamics is represented by a Lorentz attractor, a famous mathematical model that brought chaos into the light. And it's a representation of how brain dynamics is capturing models of the world and embedding them in structure that you can see here. Of course, the structure of experience is something much more complex, but it's still a dynamical model, and it still will have some kind of topology that I think we should try to understand. The second point of agents is that they have an objective function, which is what sets their goals. It's like a thermostat, a thermometer, that it quantifies how well or how bad they're doing. This, in natural agents, comes from evolution. We're here because we have a good thermometer of being alive. And it's what in KT brings the idea of valence, pleasure, and pain, if you will. So here's the agent model in a more schematic way, where you have a modeling engine that is so the agent is this box here. It's interacting with the world, receiving data, trying to model it. If there is an error in the model, it feeds back into the modeling engine. It's trying to maximize valence, its objective function. So it takes the model in and says, how am I doing? And depending on that, makes plans and sends outputs to the world. Okay? So this is the agent concept. And with it, we can now define emotion. So emotion is the model, which gives structure, plus valence. So how well or how bad you're doing in terms of your homeostasis or things like that. And finally, depression, in this context, is a pathological state of persistent low valence. You're just feeling down all the time. Your objective function is giving you a low value all the time. Okay, so this abstract framework can give us actually some interesting insights into the multiple roads into the depressed agent. So, okay, we know we have low valence. Why? Why do we have low valence? And there are many different reasons why this can happen. You may have a defective modeling engine. You may have the wrong model of the world. Your objective function, which is the one evaluating valence, may be broken. Your planning engine may be actually doing the wrong plans, so you actually start doing actions which get you into a worse position in the world. And finally, of course, the world may be a piece of shit. And that could be a trigger of depression, in fact. A traumatic event in your life gets you in a state of low valence. But if you're healthy, after some time, sometimes years, you will recover and get out of it. Sometimes you won't, because one of these may be damaged. Okay. So here's the abstract agent model. Here's the human brain. And the task now that it's part of research that we're doing is to map this into the human brain. These circuits, this modeling engine, this valence, which is associated with the reward system in the brain, and the planning engine, which is more in the prefrontal cortex. We can actually identify these functions, and based on them, we can start asking the question about etiology. Why are you depressed? Are you cognitive dyscontrol type because your planning engine is broken? Or is your objective function, your valence system, broken, and you have anhedonia, anxiety? And depending on the case, then we can actually, knowing how these systems connect between each other as networks, we can design stimulation protocols for you, for your particular biotype, and for your particular brain. So, as a conclusion, I think I would like to emphasize that model-driven solutions, this Neurotwin approach, is the future for the field. There is definitely a lot of work to do. And last but not least, the rapid advances in AI and neuroscience pose very fundamental questions that come from millennia, but I think they can no longer be put aside so lightly. Questions like, can AI systems feel emotions? And well, this is kind of a funny way of putting it, but not really. Can Roomba feel depressed? Well, if it has all the agent elements, perhaps it is feeling depression. If you cannot clean the floor because you're too dirty, or your dog is, anyways. So, and lastly, we'd like to leave you with a poem from Amy Goroff about AI. So it's just called Who Am I? And with that, I would like to thank you. This is my team. My co-founder is here too. And some of the team members are here. So thank you very much for your attention.
Thank you. Gracias. Bueno, le hemos dicho que la otra parte también enamora de Neuroelectrics. Si habéis conseguido seguir, porque me parece tan bestia lo que siempre Ana y Giulio nos han contado, me parece, bueno, brutal.